Hello everyone, this is Harry Gill, and in this video we are going to look into Java memory structure. Sometime back I had prepared a Java memory structure video, but that video was a very high level. If you are beginner in Java or don't have much experience in the Java and would like to learn the basics, so I will link that video here. Please first watch that because this video is kind of a continuation of that one, and this goes a little bit more in depth than what I have already discussed. So what we will be discussing is we will see what a program counter is. We will discuss about the JVM stacks and frames. We will see what heap memory is. We will discuss about the string pool and also the MetaSpace. MetaSpace was also formerly referred as method area. Just to show you a visual diagram, so this is what we will be discussing. Before we go into the details, let me show you the program that I will be using to discuss this one. So this is the program that we will use to discuss the memory structure. It's a very simple program. We have a main method. In the main method, we have initiated a person object. Let's go into the person object and see how it's structured. So we have a couple of instance variable. We have string, int, and also person has a car. Going into the car is a very simple class, nothing too fancy going on. And we have a empty method here. So the reason I have this program is it's a pretty random program, but it has all the things that you need to understand how the data is stored in the memory. So this program doesn't do much. Let's go back to the main class now. So once we initiate, I have initialized an int variable given a value of 10. I have a string which says is driving a car at a speed of, and then I have simply printed. So I print the name and then the log message, and also then printing the speed as 10. Here is just a random array. It's not being used, but the reason why I wanted to have it here was to show you where the arrays get stored whenever we have them. And these are the primitive arrays, so that you know how the arrays are stored, because arrays are slightly bit special. And finally, we are calling a drive method on the person object. Let's move back to the diagram. Let's first discuss about program counter register, which is PC register. So program counter register contains the address of the instruction that is being currently executed by the program. So for example, let's say our program is currently on this line, and then what we are doing here is we are assigning the number 10 into the I variable. So our program counter will have that instruction, that specific instruction being run by the program. And the program counter is per thread. We can have multiple threads in a Java program, and each of the thread will have its own program counter, because as you might imagine that threads will run in parallel. And because we want to keep track of each thread where the exact counter is, or what instructions is being run for a corresponding thread, that is why the program counter is per Java thread. If your program has 10 different threads, we will have 10 different program counters. Now let's move on to the stack. So this is the representation of a stack. Let's first discuss how the stack is created. So in our example here, so we will have a main method. As soon as a method is invoked, we will have one element created on the stack. So imagine that we just have a single element, this one, not the top. So we get one stack element created, and it executes. And when it calls a second method, like method is calling another method, then we get created a second stack element on the top. So the way it will work is, first this method has to complete. When it completes, it gives the control back to the previous one. And once this method completes, and then it gives the program back to its caller, in which our case, our program will exit because we have only two methods. So main is calling drive. Each of the stack element has something called as frame. So let's discuss here. And to discuss this frame, let's consider that this frame is of the main method, which is this method that we have written. So what does this main method has? It has a local variable called p. It has a local variable called I of the type int. We have another local variable. We are doing some actions here, which is essentially printing. And then we have an array. And finally, we call a right. So effective, the main thing to note is we have few local variables here. The way local variables of a method are stored is in the frame like so. So we have an array of local variables. So in our case, this is an array with the 4 elements. So we have a person p, which is essentially this local variable. And what happens when this particular line runs? Whenever the program see a new keyword, then that program will essentially create a person class in the heap memory. So keep note that this frame is on the stack. Now we are talking about heap. So whenever a new keyword is used, we create a instance, and that instance is created on a heap memory. Now let's examine this person. Let's go into the person class. So what does person have? So person has a string called fname, which is essentially string fname. This string fname, we have a value called John, and the value of the John is stored somewhere. We call it as string pool. So this is an important concept here. So when Java stores strings, it can store in two different places. It can store into the string pool area, or it can store into the heap area. The way Java decides to store it on string pool is that if we have the initialization and declaration like so, which is to use the string literal. So we have used, this is like we are using a string literal. We have used a double quote, we have given the value. Whenever we use the string literal, the value of that goes onto the string pool. So that's why it's being here. The reason why it does that is, so let's say in my program somewhere later on, I create another variable whose value is also John, and I create it using the string literal. Then that, the way then it will look is, so I'll probably create a, so let's create this as another person. Let's say there is another person, and that person, and it's, that person will have also a name of fname, and that fname is as per this, it's a John. Now the way it will work is this particular fname will again use the same value. So you see, we haven't created a duplicate. So it's not like Java will create a duplicate John and then it will point it to another one, but it's actually reuses the same string value that it created. So there won't be any duplicates. Also, I want to highlight that this John doesn't need to be the value of person and fname. It could be any string in the program. So let's say if I do string A is equal to John, then A will start pointing to John. There doesn't need to be any correlation between the other variable. The main important thing is both the variables have the value as John. Now in future, let's say what happens if you change this particular f name, let's say you change its value to, let's say, Peter. It doesn't change it here. When then Java realizes that now the value of this f name has changed, then it's going to create another value called Peter, and then it will change the reference of that one to Peter now. So you might have read some in many places while doing your studies that strings are immutable in Java. And this is exactly what it means, that once you create John, you can't modify that. Yes, you can modify the value of f name, but you can't go ahead and change this particular value to Peter or anything else. This will, once this is created, it will always stay John. So this is essentially how the string will represented when it's created using the string literal. Now, how about if we use a new keyword, because we can create string using new keyword, just like we created a person, we create a string using new string and then give the name. When we create the string using the new keyword, then a string instance is created on the heap. See, it's now not getting created on the string pool. It's getting created on the heap. And the L name, which is essentially our variable here, will now start referencing to that object on the heap. So this is created on the heap itself. So in this case, when a string is created using the new keyword, then the string object is no different than any other object that we create using a new keyword. So which means if I do string s is equal to new string do, then we will have another instance on the heap. It won't refer to the same instance that we created previously. How about the primitive type? In this case, it's int, but the same is true for byte, long, and other primitives. When we have the primitives, it actually gets stored on the heap within the class structure. So it doesn't create a new object on the heap because this is primitive. It's actually stored within the class that is created on the heap. Now let's discuss about the car instance in the person. So this is the representation that we see here in the diagram. So car is pointing to a car instance because we used a new. So that's why a new object has been created on the heap here. And when you go into the car, so we have a make variable of the type string, and the value is assigned using the string literal. Now going back to the memory representation, so we have car. The make variable is actually going to the string pool here because we have used a string literal. And this is how the person object will look like. So person will have f name pointing here, L name pointing to here, age will be stored within the person, the car reference will be pointing to the car instance, and the make will be pointing to Chevy. So this is all that's done when in the main method we call person p is equal to new person. So that's how the memory structure looks like. Now coming to the next line, int I is equal to 10. Now notice that we are in the main method. That means we have to go back to the stack or the frame here. Whenever we have the primitive variable within a method, where like primitive variable is a local or to that method, then the value of that is stored within the frame. That's why when you read, you will see that the primitives are stored on the stack. So essentially within the stack, they're stored on the frame. So we don't have any pointer going out of this into anywhere. So the value 10 will be stored actually on the frame. Now moving on. So we have a string variable called log message, and you see this is created using a string literal. And as we have already discussed, the log message will be pointing to a value that is stored in the string pool. So this is string pool is driving a car at a speed of. And this is just an instruction to print. So when this is run, it will get the f name, which is, so it goes to P is here, to f name, to John, and then the instruction concatenates log message. And as we have seen, it will go to the log message, will get the value from the string pool. And the next instruction is to concatenate I. I is a local variable, which essentially means it will simply get the value from the stack itself. And it will print a line saying John is driving a car at a speed of 10. So now that println had all the information that it needed to print. Now coming to the next line here. As I mentioned, this doesn't do anything, but I have it here to show you how the arrays are represented. So in this case, I have an array called A. It's a primitive type of array. So it's a array of ints. If it's a primitive type, then the value 10 is stored on the stack. But if it's an array, even if it is primitive, the array is actually always stored on the heap. So we have A here, which is int array, and let's follow this line. And the way this particular instruction will be represented is like so. So we have an array, the value 20, the value 50, and the value 60 are stored on a heap. So even though they are primitives, they are still stored on a heap, not on the stack. The reason is because arrays is considered as an object or an instance, and instances are always stored on heap. Just like person, how we have that age 25, 25 is a primitive, we have it on heap. Similarly, 20, 50, and 60 stays on the heap. Now let's move on to the discussion of what a method area is, which is also called now as MetaSpace. Think of this space as storage of the compiled code. So whenever you write a .java class, the .java class gets compiled into .class file that has the bytecode. When the loading of these classes happen, the program gets loaded into this area. So essentially, this is a storage of compiled code. Each of the class will have its byte representation, which is stored in this method. So in this example, I have shown class A, but in our example, you can think of it as the main class, the person class, and the car class will have their own bytecodes stored in this area. Each of the class will also have something called as runtime constant pool. Honestly, I didn't quite understand the specific of runtime constant pool, but what I have understood is that whenever we have a class level variables like static variables, then those static variables are not stored as a part of the bytecode, but they are rather stored into a symbolic table called runtime constant pool, and the bytecode simply refers to that. Now note that the runtime constant pool, if it's a primitive, it will have the value, but if it is a reference, so let's say we have a static car in the person, then the actual car instances will be on the heap. But in this runtime constant pool, we will have the car, and the value of that car will be the address of heap where the car instance has been created. And this runtime constant pool can be referenced from the frame. So frame will have a pointer to that particular class's runtime constant pool. Now let's discuss about the operand stack. So what is this used for? So each frame will have its own operand stack, and the reason why operand stack, or the place where operand stack is used. So let's say we have an expression int k is equal to 5 plus 10. So we are effectively doing some calculations here. Within the bytecode, first of all, this expression is represented let's say, as a postfix notation, in which case in the bytecode we will have it as 5, 10 and plus. So this is a postfix notation where the operator comes after the operands. When this instruction is executed, that is when the operand stack comes in play. So whenever 5 is encountered, 5 is pushed into the stack, the operand stack, and next we encounter 10. So 10 is essentially again an operand, so it will be pushed as a next element of the stack. But when it encounters the operator, and plus is a binary operator, it needs 2 operands, then 10 and 5 are popped out of the stack and then they are computed, which is 10 plus 5 becomes 15. And in our example, that 15 gets assigned to k. So effectively, the operand stack is used for calculations, for the computations. So this is effectively how the whole frame is looks like from the memory perspective. Now let's come into from the execution perspective. So whenever a frame finishes, so frame essentially represents a method. So whenever a method is executed, when it hits the last line or a return of the method, then that particular frame is popped out and the execution has to go, or it has to be returned back to the calling. So the current executing frame has a responsibility of restore the data of the previous frame, because the previous frame will have a similar type of data. So it will have array of local variables, it's going to have operands and also a reference to the runtime constant pool. It's a responsibility of the current frame to restore the state of the previous frame so that the execution can continue from wherever it left. And that is where the program counters come in play as well. So just to give you an example, so when we have p.drive, so which is essentially this frame, so whenever it ends, it needs to return back to its previous frame, which is main in this case, and it needs to set all these operands and local variables and whatever the state of that main was when drive was called. And also it's going to tell the or increment the program counter to go to the next instruction so that it doesn't start executing from the top. So effectively, the main point is that the way or the currently executing frame will have responsibility of maintaining or restoring the state of the previous one, and so on. When this frame execution finishes, it restores the previous one and until it goes to the very first frame, after which the program will end. So that is all I wanted to discuss. I hope this would have made your concept of memory structure a bit more clearer when it comes to Java. If you have any specific questions, please let me know in the comments. And if you like the video, please hit the like button and subscribe for getting notification of the upcoming videos. Until next time, thank you so much.